This lesson follows on from the two introduction lessons that you had from Mr. Vaughan about polar coordinates. So you will already have been looking at curves, looking at sort of drawing curves when they're defined in polar form and what they look like. So if you have a curve drawn in the same way as you can with normal curves, you can find the area enclosed by curves, but when they're written in polar form. So let's go on and have a look about how we do that. Okay, so I'm going to just quickly derive the formula for you just by talking you through it. We know from the work we've done in our standard maths that if you have a circle of radius r and you have a sector of the circle where the angle at the centre is defined theta in radians, we know that the area is half r squared theta. That's one of the formulae that you learned when you were doing radians in your standard maths. Now, if I think about a polar curve, I appreciate not all polar curves are circles, but if we look at a change in angle theta from theta to theta plus delta theta, so a very small sector, okay, then we can say that the area of that sector is approximately with a curve around the edge that looks like a circle, okay, so that little tiny sector will have area half r squared theta. Okay, so if we then, in a similar way as when we do integration and working out what integration is all about, if I integrate these little tiny sectors over the interval between theta 1 and theta 2, then this gives us the formula for the area of a curve defined in polar form. So it's going to be half the integral between the limits of, notice we've got r squared d theta there, okay, and this is the curves defined in a polar form, r equals f of theta. Okay, so that's where the formula comes from. So what you're going to do now is write that down in your notes. Okay, so this is what the formula looks like. This is what it looks like in the formula book. Okay, it is defined on page 9 of the formula book, so it's not something you need to learn, but you need to know where it is in the formula book. Okay, so important things to notice with this. Okay, we're doing integration to find an area, but look at what our limits are. Our limits are values of theta. Okay, so when we're finding an area, instead of integrating over either vertical lines if we're integrating with respect to x, or horizontal lines if we're integrating with respect to y, instead of that, what we're doing is we're integrating between lines that come out from the pole there. Okay, so when you're looking to see what your limits are going to be, what you're thinking about is lines or half lines that come out from the pole and go out and meet the curve. So it gives us sort of little sectors of our polar curve. All right, so that's the difference really that you must think about when you're doing integration for polar curves. Now, because the formula, it's got the half at the front, but it's also got an r squared in. Now, you know a lot of the polar curves that you've looked at have been r equals something to do with sine theta or something to do with cos theta. So when we go on and use this formula, because we square the function r equals, we quite often get sine squareds and cos squareds. Now, we've come across some of those before. I'm just going to remind you what you do for integrating those. Again, this will be something you do in standard maths later on, so it's good for you to be practicing it now. So what we do when we integrate sine squared or cos squared is we make use of the double angle formula. Okay, so the formula we use, they're both double angle formula for cos. So the first one is cos 2a is 2 cos squared a minus 1. Okay, and the second one is cos 2a equals 1 minus 2 sine squared a. So what you do is if you're integrating cos squared a, you take this one and you rearrange it to be cos squared a, okay, equals a half times cos 2a minus plus 1. Okay. And similarly, if you're integrating sine squared a, what you do is you rearrange this one to say sine squared a is a half times 1 minus cos 2a. And you'll see when I do questions that I always write these out and rearrange them just so I remember, have I got a plus or have I got a minus in it? And then you'll need to set the argument here according to whatever this argument is here. Okay, all right, so what we need to do then is have a look at some examples. Okay, so let's have a look at example number 1. So find the area enclosed by the cardioid with equation that. Now, what I suggest you always do with these is to just draw a quick little sketch, okay, so we can think about what that cardioid looks like. Okay, you will have seen when you were doing sketches before, the first thing I always do is look for my tangents to the pole. Okay, tangents to the pole, remember, are where r is 0. So I set my function r is 0 and I get cos theta equals -1. Okay, so cos theta equals -1, pop it in your calculator, you get theta equals pi. So this curve, remember what the cardioids were, theta is pi is this line here, so it's going to look like that. Okay, it doesn't need to be an amazing sketch, it's just for you to think about when you're integrating. So we know that the formula, do state the formula, area equals half, remember the half, integral, remember the r squared. Now, we can make use of symmetry to make our integration easier. Okay, yes, we could integrate from 0 to 2 pi, but quite often using symmetry means that you can use values for limits that are just a little bit easier. So what I would do is, because it's symmetrical about the horizontal axis there, is I would use symmetry to say that my area is 2 lots of the integral between 0 and pi. So can you see that the integral between 0 and pi will give me my shaded bit, and it's 2 lots of that because it's symmetrical below the axis. Okay, so what I'm going to be squaring is all of this, so I'm just going to stick it in a bracket for now. It's all of that squared. Okay, so remember your d theta as well. So make sure that you square all of that. You can see the 2.5 cancel. Now my a is constant, so I'm going to just pop it outside my integration. And remember, I've squared it, so it's an a squared. Now, when I expand my 1 plus cos theta, I must expand it as a double bracket all squared. So I get cos squared theta plus 2 cos theta plus 1. Okay, so this is where I need to use my double angle formula. So what I will do is I always write it out. So cos 2a equals, I'm integrating cos squared, so I need the 2 cos squared a minus 1. I'm going to rearrange it to say cos squared a equals cos 2a over 2 plus 1 over 2. Okay. So I'll write that out and then I will substitute that in, okay, for my cos squared theta. Okay, so that goes in for my cos squared theta, so this is replaced by this. So cos squared theta, so a is equal to theta, so this will be cos 2 theta over 2. I've got a plus a half, but look, I've also got a plus 1 here. So I'm going to combine those together at the end. So I'll put in my 2 cos theta. You can keep them separate if you want, but it's easy to combine them. 1 plus a half gives me plus 3 over 2. It just gives you one term fewer if you combine them together here. Right, now you've got to remember about your integration. I do appreciate you've not really done trig integration, but you need to just know the basics for this. Okay, integrate. Cos goes to sine. It goes to sine of the same angle. Now we've been doing the chain rule, haven't we, in our standard maths? So remember, when you differentiate, you times by 2 because it's a 2 theta. When you integrate, you divide by 2. So that becomes a divide by 4. Okay, do remember those. Cos goes to sine. And 3 over 2 is just a constant. So we're integrating with respect to theta. So it goes to 3 over 2 theta. Okay. Right, I keep going on to you. Show your apply your limits mark. Okay, so I've got sine of 2 pi over 4 plus 2 sine of pi plus 3 pi over 2 minus, now when I put in 0, sine of 0 is 0 and that's 0, so I'm happy enough just to pop a 0 there. Use a calculator if you want to. Sine of 2 pi is 0, sine of pi is 0, so I end up with 3 pi a squared over 2 as my answer, and you leave it in exact form like that. Okay, right, example number 2 then. Let's go on to example number 2. Find the area of one loop of the curve with the polar coordinate r equals a sine 4 theta. Remember when you did your sketching your curves, okay, things that have just got sine of a multiple angle and cos of a multiple angle give those lovely flowers. All right, so sine 4 theta will have 4 loops, okay, but we need to know where those loops are. So again, I'm going to do my sketch, just a really quick sketch, and the first thing I'm going to do is I'm going to look at my tangents to the pole. Okay, remember what they are where r is 0. Okay, so I'm solving sine 4 theta is 0. Okay, so I'm going to get a few answers. Okay, 4 theta equals, well, I get 0, I get pi, I get 2 pi, and I get quite a few more. Okay, but I'm only going to need the first couple really to enable me to sketch this. So my first tangent to the pole is 0 and my second one is pi by 4. So if I was to sketch it like this, okay, I've got a tangent to the pole here, I've got a tangent to the pole at pi by 4, so my loop would look like that. Okay, so that's when I want to find the area of that one loop. You can see from my sketch what my limits are going to be. They're going to be between 0 and pi by 4. Okay, let's quote my formula. So area equals half integral r squared d theta. Okay, let's pop in my r and pop in my limits. We decided from our sketch it's between 0 and pi by 4. Be careful with r squared. You do get an a squared as well. Don't miss that bit out. Sine squared 4 theta. So again, you can see it comes up a lot. We're going to need to use our double angle formula again. I'm going to write it out. It's always cos 2a. The one with sine squared is 1 minus 2 sine squared a. So when I rearrange that, I get sine squared a equals a half minus cos 2a over 2. So that's what I'm going to replace in my integral here. Again, I'm going to pop my a squared outside. Okay, just keeps it tidy. Now do be careful, okay, where you're deciding what your argument needs to be. Sine squared of 4 theta. So this is 4 theta. So this here will need to be 8 theta. Okay, do look carefully for that. So my sine squared 4 theta is replaced by a half minus cos 8 theta over 2. All right, so just be careful when you use your double angle formula that you're replacing the argument with the right thing. Let's do my integration. Square brackets. Half goes to theta over 2. Cos goes to sine of the same argument. Don't forget, because it's 8 theta, I get the divide by 8, so that will become over 16. Okay, apply my limits mark. So pi by 4, that becomes pi by 8 minus, what's that going to be? That's going to be sine of 2 pi over 16. Okay, and then minus, all of that's going to be 0. Again, the sine 2 pi bit becomes 0, so you end up with pi a squared over 16. So notice it's got an a in it because our original equation had an a in it. So write out your working nice and clearly. Okay, use your double angle formula carefully. Make sure you replace the sine squared argument, okay, with double it when you do the 1 minus cos 2a over 2. Okay, one more to have a look at then before it's over to you. Exam style questions, you can see how many marks it's worth. Shade the region R for which the polar coordinates r theta satisfy that. So what I'm going to need to draw first is I'm going to need to sketch r equals 4 cos 2 theta. So again, what you'll notice is what I'm going to do is I'm going to think about where my tangents to the pole are. Now you know, just got a cos 2 theta, so it's going to be flowers with 2 petals. Okay, tangents to the pole r is 0. So we get cos 2 theta equals 0. Okay, so we get 2 theta. When cos 2 theta equals 0, we get pi by 2, and we also get minus pi by 2. Okay, so you can see actually the range of values that they're talking about there is going to be that first petal. I'm going to just draw up here. Make sure your sketch is a reasonable one though, because there are a couple of marks there. So it's going to be like this. Okay. Theta, pi by 4 and minus pi by 4 are my tangents to the pole. So let's sketch them in. Up there, my pi by 4, down there. Yours is going to be much better than this, okay? And then it's going to be my petal with a round end like that. How far does it go out? They'd expect to see that 4. Okay, now it says shade the region for which r is less than that curve. R is less than that curve is going to be inside my curve, so it's going to be inside my petal there. Okay, right, good. So now on to part B. Part B is find the area. So let's write our area formula. Half integral r squared d theta. I'm going to again make use of symmetry. Okay, so by using symmetry, because it's just a cos curve, it's symmetrical about the horizontal axis. So I'm going to find just that red shaded bit. Okay, so between 0 and pi by 4, and then I'm going to double it. Okay, so I'm going to say it's 2 lots of half integral between 0 and pi by 4. Okay, of r squared. Do be careful, r squared. You need to square the 4 as well. So you've got 16 cos squared 2 theta. Okay, so do remember to square the 4 as well. Double angle formula again, comes up a lot. Cos 2a, 2 cos squared a minus 1. Okay, so cos squared a is equal to cos 2a over 2 and then plus a half. Okay, so that's what I'm going to sub in here. Okay, so what you'll notice is, think about the argument though, cos squared 2 theta, this is a 2 theta, so this must be a 4 theta. That's the sort of thing you've got to think carefully about. Now it's 16 lots of that. Okay, so I'm going to end up with 8 cos 4 theta, because it's 16 times that over 2, and I'm going to end up with plus 8 d theta. Okay, so you're happy with what I've done there. The 2.5 cancel. I've done 16 times this, so the 16 becomes 8 because of these halves here. Okay, right. Let's do our integration then. Cos 4 theta goes to sine 4 theta. Do remember the over 4 though. Okay, and the 8 goes to 8 theta. Pop in our limits. 8 divided by 4 gives us 2, so I get 2 sine of pi plus 2 pi minus 0 for both bits. Sine of pi is 0, so what do I end up with? My answer is 2 pi. So you can see those 3 examples what's useful is to draw a sketch, look at the area that you're trying to integrate, make use of symmetry as well, because it can just make applying those limits easier if you can make use of symmetry for your, especially for your cos functions. Okay, and make sure you're happy with the double angle formulae. Okay, so this is the first lesson on finding the areas. So I'm just going to set you these questions from the exercise. Okay, and what we're going to go on to next lesson is finding the areas between polar curves. So a little bit like with your normal integration where you'd find the area between two curves. So we'll go on to that next lesson. So these are the ones I'd like you to do, please. Okay, but you don't need to submit any of those, but do mark them from the back of the book. Okay, thank you very much.